This is a review lesson for plate tectonics, which will be on the unit test upcoming. Starting, let's take a look at our 60-second writings for last week. The first one, last week we learned, the week before obviously, that convection currents in the mantle move the plates, which causes earthquakes and volcanoes. Knowing this, where do you think there are plate boundaries in or near the United States, or other places in the world? In class, you had 60 seconds to respond to this. If you want to practice it, you should pause this video now and do that. This is a map of the plate boundaries, which you've probably seen. It is from the textbook. And if you look at it, you can see the Earth being divided into, I believe it's 12 major plates and many minor plates. We talk about the Ring of Fire. The largest plate is the Pacific Plate, and the most active boundaries are generally the subduction zones, which we will talk about later in this video. So big earthquakes and volcanoes here. And hopefully now, as you have spent some time working on your projects, some of these places will look more familiar to you. Many of the large plates correspond with the continents, like the North American plate, or the African plate, the Eurasian plate, South American plate, some of these also including parts of the ocean. And then we also have smaller plates, the Philippine plate, the Juan de Fuca plate, Nazca plate, so many smaller plates that also get kind of smashed into by other plates. Another one of our writings in this week was, what evidence did Alfred Wegener have to make his hypothesis that the continents are moving and had once been one giant supercontinent? And why was his idea not accepted until about 50 years later, after his death? Once again, you might want to pause this recording and answer this for yourself. It is the kind of thing you might see on the unit test. Alfred Wegener came up with his idea around 1910. Really not that long ago in terms of science. And then it became much better accepted in 1960. The answers, the reasoning here is this. Alfred Wegener, and again, there are three main lines of evidence that Wegener had. Let's see if I have them here. Three main lines of evidence that Alfred Wegener had was that the continents, so his idea was that continents are moving, called continental drift. What evidence did he have? Well, one line of evidence is land features, which are things like mountain ranges that matched up on opposite continents. Another one was fossils, fossils of similar animals, and I'll show you a map here in a minute, and evidence of climates in the past. And this isn't just climate now, but many of the areas that are now, say in Antarctica, show fossil evidence of having been in a much warmer climate, which is partially because when the continents were all together in a giant supercontinent called Pangaea, which means all Earth, when they were all together in that one giant continent, that whole supercontinent was higher up. Why nobody believed him? At the time, he could not explain what force could possibly move continents. So he could not explain how this could possibly be happening. On a lesser note, he also was a weather scientist, not a geologist, and so that worked against him as well. Let's take a look at the continents. I'll come back to that one. The continents, we looked at this map in class. We saw that some of these continents seem to fit together quite nicely. That was one of the first bits of evidence that he saw. And it made him curious about it, and he looked for further evidence after that. So Africa and South America most obviously, and then the fossil evidence, there were things that matched up, and again, not perfectly due to erosion and a number of other things, but evidence of fossils, evidence of coal beds, And you can see evidence of mountain ranges, either present or past. And you can see how things fit together and then drifted apart. And so he said, maybe there's some force pushing these, and as we'll find out, we do believe now that is in fact true, and we now have a pretty good explanation as to why that might be happening. Okay, so here, continental drift hypothesis, plate tectonics theory, and seafloor spreading. Let's take a look at what's next. Okay, our next 60-second writing was, what is the difference between a hypothesis and a theory? For example, continental drift was Alfred Wegener's hypothesis, and about 50 years later we come up with plate tectonics theory, which is what we teach here, and also what is in textbooks. So what is the difference between a hypothesis and a theory in general, and specifically for the plate tectonics? Again, you might want to pause the video so that you can answer this for yourself. A hypothesis is an educated guess and it oftentimes is based on what you see, but a hypothesis is then set up so you can test it or explain it better. Now with continental drift and plate tectonics, it's a bit difficult to, say, set up an experiment to test it, but in plate tectonics theory, it has many of the ideas of continental drift. The big difference is that it is now well accepted by all scientists. And the reason why it is well accepted is that, as you might remember, one of the problems with Alfred Wegener's ideas is that he couldn't really explain what could possibly move the continents. And so over the years between 1910 and 1960, scientists did find strong evidence that of what could be causing the continents to move, which has to do with convection currents in the mantle. And so our next question is going to be about seafloor spreading and what evidence we have there and how that confirms what Alfred Wegener hypothesized and brought it to be plate tectonics theory. And so plate tectonics theory, scientists now believe, is really the best explanation for what we see happening. And it does have evidence that can be repeated or confirmed. This is just another image from the textbook showing the kind of Pangea, all Earth, the continents all together, and showing some of the different lines of evidence that suggest that it was in fact all together. Along the mid-Atlantic ridge, which we now know to be a plate boundary, a divergent plate boundary, which we'll talk about in just a minute, not only did we find evidence here that the plates were moving, but if in fact they are moving apart here, that also continues to confirm Wegener's idea because it pushes South America away from Africa in exactly the way that Alfred Wegener hypothesized might be happening. These different plate boundaries, again, are showing some of the many boundaries in which direction things are moving. Mid-ocean ridges, in green, are where they are moving apart from each other. Deep ocean trenches, you might remember, are formed at subduction zones, where the two plates are pushing together. So again, you can see, going through this image, which is also from the textbook, what seems to be happening with plate tectonics. Seafloor spreading. Seafloor spreading is the evidence that was needed to show that the continents are moving, to show what force could possibly move the continents, and demonstrate, in fact, that it is still happening today. At areas like the mid-ocean ridge, we have oceanic crust, so at the bottom of the ocean, and we have molten material here, volcanic activity, and here at the ridge, you're getting volcanoes, you're getting lava, all sorts of activity happening here. Now, how do we know, in fact, that these are moving apart from each other? Well, scientists, and in the 60s first, they saw, or 50s, they saw this first with sonar and drilling samples. But if you look at there's almost like stripes in the ocean floor. And over here, and over here, there is new rock. And they can date using radioactive dating. This sample and this sample are the same age, which suggests they were pushed away from the center at the same rate. And similarly, they can look at things farther away, whatever X distance, however many miles, and again, date it, and it does confirm that they are the same age at the same distance. So this is one piece of evidence that supports this. Another one is very interesting. It has to do with magnetic field that is magnetic fields of the Earth. The directions are preserved in the rocks. This is a little more complicated, but basically when the melted rock, when the lava is melted, when it's magma, uh, it can basically be formed into a magnet that is affected by the Earth's north and south poles. And in a very strange development, it turns out that the north and south poles of the Earth, some points over the history of the Earth, have switched. So what we think of as north had the south, and this was north. So say south is negative charge and north is positive, they were reversed. And because new material keeps being formed, you can actually see these magnetic stripes being preserved in that rock as it cools. A little bit confusing, but again, it's evidence that does in fact confirm the constant creation of new crust at this ocean boundary. If you want more details on that, you can double check in the textbook. The level of detail you need to know is basically just that there are a number of lines of evidence that confirm that this new crust is being formed at a somewhat constant rate in a number of areas. And then to kind of complete the cycle, new crust is being formed. So you might think, well, is the Earth just getting bigger and bigger, and why isn't the crust just wrinkling up? Well, it turns out that at the mid-ocean ridge, crust is formed. And then when it hits the continent, remember the continental crust is less dense. And because of that, it kind of floats on top. The oceanic crust gets pushed underneath and destroyed. So here you have old crust is destroyed, and actually you get volcanic action here, and here new crust is made. Again, further evidence of continental drift and plate tectonics. Next, we'll talk about the three major types of plate boundaries. There are divergent boundaries. Divergent means to move apart. Convergent boundaries and transform boundaries. As we look at this, divergent, they are moving apart. And on a further slide, I'll have a bit more detail than this, but just for the very quick overall, convergent boundaries, converge means to come together. The plates are moving together, and we'll talk about some additional detail on that. And transform is the one that doesn't easily explain. Transform boundaries are moving side by side. So, divergent boundaries. You can either have oceanic crust. This happens at a mid-ocean ridge. And as we talked about on the last slide, at the mid-ocean ridge, we have new crust being formed. So new crust is formed. It is a constructive boundary because we have new rock being formed. If you have continental, so on land instead of under the ocean, we get something called a rift valley. And a good example of this, a rift valley, is found in Africa. the African Rift Valley, it's called. And again, there's volcanic activity where these two plates are being pushed apart. You might remember in class, we also looked at some Google Earth images, and so you can do that on your own time and identify some of these boundaries. Secondly, the convergent boundary. You can have, again, a couple subsets of this convergent boundary. First of all, you can have continental crashing into more continental. So continental crust, moving into each other. And here we get mountain building. And so the crust is just pushed into each other and pushes upwards, making mountain ranges. And again, that's continental, continental. The same thing would happen if both plates that are moving towards each other are oceanic. They're of the same density, and so they just kind of move upwards. Then, probably the most interesting boundary is when you have a continental piece of crust crashing into an oceanic piece of crust. And so this, of course, is supposed to be an arrow here. But continental crashing into oceanic, what happens here, it's a destructive boundary. We call it subduction. You can remember that. Sub means below. So subduction, it's pushing it below. Submarines go underwater. The subduction zone is in the ocean. So as you see here in our picture, the oceanic crust gets pushed under the less dense continental crust, and as we saw in the other picture, as the oceanic crust gets pushed into the mantle, it melts, heat, pressure, and you get volcanoes. Finally, we have the transform boundary, and you see here I don't have a tremendous amount of detail, but it can be either continental crust, oceanic crust, but in either case, the crust is neither created nor destroyed because it is moving side by side. A stunning example of this is the San Andreas Fault in California, which is, depending on what source you read, between 300 and 800 miles long, and is responsible for all of those famous and infamous California earthquakes. So crust is neither created. In class, we also watched an earthquake video that talked about the very devastating earthquake in Haiti in 2010, and that earthquake also happened along a transform fault. So although crust is not destroyed, they certainly can be very destructive natural disasters. Here again, this was another one of our 60-second writings, but again, looking at this map that we already talked about, being able to look at a map and predict which direction the plates are moving. I believe that is it for plate tectonics. You can, for the next lesson, you can check out the flip lesson about volcanoes.